Hi everyone, welcome back to another video. In today's video we will be focusing on signals and systems, specifically on how to find the energy and power of a signal. So for this first question that we have here, we're trying to find the energies of each energy signal. And so in order to do this, we need to break down the signal that we have. So we'll go ahead and call the function x of t, and we can see that we can break it down to parts. So going from 0 to 2 here, we can see that we have a linear function which is just 1. So we can say 1 from 0 is less than or equal to 2 is less than 2. And then we can see for the second part here, it's just negative 1. So negative 1 from 2 is less than or equal to t is less than 3. And then we know it's 0 otherwise, and the reason being for this, we can see it's just 0 here and also 0 here. So those parts won't really matter. So at this point, this is where we will use the energy formula, which is the following. So we can say energy is equal to negative infinity to positive infinity, the absolute value of the function, squared dt. So this is an integral, so you need to know basic calculus for this. And so we can go ahead and plug in what we have here from the function into this formula. So an important thing whenever we're using this formula, we won't be using negative infinity to positive infinity anymore as our bounds for the integral. We'll instead be using these bounds right here, 0 to 2 and 2 to 3. So we'll go ahead and plug those in. So we have from 0 to 2, it's just 1 squared dt plus from the integral of 2 to 3, negative 1 squared dt. And so I dropped the absolute sign here just because these values here will be positive no matter what because of the squared value. And so simplifying this and also just doing basic calculus all at once, we know that just dt, the integral of that is just t from 0 to 2, plus, once again, t, because negative 1 squared simplifies to 1, and that becomes t, from 2 to 3. And now, we need to say 2 minus 0 plus 3 minus 2, which leaves us with 2 plus 1, which is equal to 3 joules. So, this is how you find the energy of the signal. Pretty easy enough once you get enough practice. So same principle applies here for part B. So we'll go ahead and break up the signal into its parts. Now this is the opposite of last time. So as we can see here, the first time we have positive 1 from 0 to 2. Now it's negative 1 from 0 to 2. So I'll go ahead and write that down. And once again, vice versa. So we can see it's negative 1 the first time. Now it's just 1 the second time for a balance of 2 to 3. And 0 otherwise. So using the same formula from last time, I'll go ahead and write it down again so we have it here. Now just by looking at the function that we have, we can assume that the answer will be exactly the same. It'll just be 3 joules for the energy. And the reason being is that this is an absolute function. So plugging in these numbers, we will see that that does happen. So we have from 0 to 2, negative 1 squared plus the integral of 2 to 3, 1 squared, forgot to put my dt. dt is then equal to t from 0 to 2 plus t from 2 to 3. And that will give us 2 minus 0 plus 3 minus 2, which is equal to 3 joules. So same thing, pretty easy. Here's another one that we'll move on to that's a little bit more difficult. And so this is different from last time. So to break this function down, we'll just use some basic algebra here. So we can see that our y value is -1 and our x value is 1. So taking the slope of that, we know that that's just -t. So we can say -t, and the bounds for that are from 0 to 1. So we know 0 is less than or equal to t, it's less than 1, and is 0 otherwise. So we'll go ahead and plug this into the energy formula like last time. And let me get that here just to make sure we have it so we don't get confused. And so we'll plug this in. So E is equal to the integral of 0 to 1 -t squared dt. And so simplifying this, -t squared is simply just t squared dt. And then using calculus, we can say this is 1/3 t cubed from 0 to 1. And then 1/3 of 1 cubed minus 1/3 0 cubed. Well, this just goes to 0, so we're left with 1/3. So the hardest thing about finding the energy of a signal isn't necessarily plugging into the formula, but just recognizing how to obtain the function for it. Now this last one, probably the toughest one yet. So how do we find the function for this? So like last time, we can see that it has a slope of 1. So it's just t. But we see that it starts at 1 instead of 0. So we know from algebra that we can shift functions. So what this means is that we have shifted to the right 1. So instead of it just being t, we have t minus 1, because that means that we have a shift. And that might sound a little confusing of why we do that. And the reason for it is whenever you set your function equal to 0, that gives you a positive value. So that is why whenever you see a t minus 1, it shifts it to the right. Or if this was a plus value, for example, it would instead shift it to the left. But for this example, it's shifted to the right. And so the bounds for this is from 1 to 2, which we will put here, and 0 otherwise. So go ahead and plugging in what we have here. We have the energy formula. So we can say E is equal to the integral from 1 to 2 t minus 1 squared dt. And so in order to take the integral properly, we'll go ahead and factor t minus 1 squared, which will be t squared minus 2t plus 1 dt. And so taking the integral of that, we will end up with 1/3 t cubed minus t squared plus t from 1 to 2. And just like last time, we'll get 8/3 minus 4 plus 2 minus 1/3 minus 1 plus 1, which will give us a result of 1/3 joules. So kind of the point of this exercise is to show also that even if it's a shifted function, if it has the same slope, then it will give you the same energy. Now for our last example here, we'll focus on the power signal formula. And this is a periodic signal, so we know to find the power for it. And first things first, we need to find the period of the function. So we can see here from our boundary values, we have a -2 to 2. So that means we have a period of 4 seconds. Now the power formula is a little different from the energy one, which is as follows, where it's 1 over the period, the integral of -t over 2, t over 2, and then your function squared dt. So kind of similar, but at the same time different. So whenever we plug in our values here, we can see that we get 1/4 because we're just using our period value here for here. Integral from -2 to 2 because -4 over 2 is -2 and 4 over 2 is just 2. And so our function here is found right here, t cubed. So this will be t cubed squared dt. And using exponent rules, we can simplify that. So that will be t to the 6 dt. Because whenever you have your exponents in this fashion, for example, you get to multiply them together. And so whenever we do some calculus here, we can find that is reduced to this, -2 to 2, and doing some more simplification here, I can say 1 over 28, and how I got 1 over 28, I just did 1 over 4 times 1 over 7, which is equal to 1 over 28. So that will help with the simplification process here. And so now we have 1 over 28 times 2 to the power 7 minus 1 over 28 times -2 to the power 7, which is 128 over 28 plus 128 over 28, which reduced will give us 64 over 7. So there you go. This is how you find the power of a signal and also the energy of a signal. This is kind of basic, but the key here is just to be able to recognize what the functions are. And once you're able to do that and find the boundary values for it, you can just plug in the values into respective formulas and you'll get your answer pretty simply. Hope you enjoyed this video. I hope it's helpful, and I hope you have a good rest of your day and have a good week.